I'm Anthony Bedner, a research chemist with the U.S. Army Corps of Engineers Environmental Laboratory, and I do analysis of nanomaterials using field flow fractionation interfaced to inductively coupled plasma mass spectrometry. Field flow fractionation, or FFF, is a useful analytical technique for nanoparticles because it provides very high definition size fractionation of nanoparticles in a variety of aqueous matrices. When you couple the FFF separation technique to a very elemental specific detector such as ICP-MS or ICP emission, you can get elemental specific detection of nanoparticles at the part per billion after the fractionation has occurred. Field flow fractionation is a chromatography-like technique that separates nanoparticles based on physical forces rather than chemical interactions with a substrate or a media. Specifically, in this column, you have a very thin channel that's about 1/4 of a millimeter thick and about 30 centimeters long. In that channel, you have two flows, one going down the channel just like chromatography flow would be. The second flow is perpendicular to the channel, which shoves the particles against the accumulation wall. These particles will diffuse against that force based on size, specifically diffusion coefficient. The smaller the particle, the farther the particles diffuse against that cross flow. Therefore, they get taken up higher in the channel and taken out faster by the channel flow. This gives you the separation based on size. We then take the effluent from the channel and send it to the ICP-MS, which provides elemental specific detection at the part per billion concentration range. The first detector we use is a UV absorbance detector, primarily for organic compounds as well as the polystyrene size calibration standards. The second detector is the ICP-MS. This is where a 7,000 degree plasma takes the particles and ablates them into ions. The rest of the instrument determines the mass of those ions, where we can do multiple elements simultaneously. For example, the test analysis we'll do today is silver nanoparticles, where we are going to look at 2 isotopes of silver as well as 1 isotope of gold, which is the seed used to create the particles during the synthesis procedure. Today we're going to use FFF ICP-MS to look for gold seeds inside nanosilver particles. We have here a mixture of nanosilver that contains gold seeds. I'm going to take a sample and inject it into the FFF. Now that the particles have been injected into the FFF, I tell the ICP-MS to start the analysis. This is the beginning of the trace from the ICP-MS for the particles we just injected. This first peak that you see here is what's called the void peak and represents unretained material in the FFF channel. This can be either very small nanoparticles around 1 or 2 nanometers or dissolved species such as silver ion. The sharp peak you see developing here is the first peak from our nanoparticle mixture that we injected. As you can see, there's silver present in a much larger abundance than gold because the gold is just the tiny seed within the center of the silver nanoparticle. So this is the FFF data after the analysis. And as you can see, we have 2 peaks that represent the mixture of particles that we injected initially. The first particle is the smaller one, and it has the gold core that we hypothesized was present. The second peak is the larger particle and has no gold core. So this gives the power of the FFF ICP-MS to determine the elemental constituents of nanoparticles. So after the data is collected, we use the calibration standards to determine the size of the particles that eluted from the FFF. And then we compare them to the pre-exposure samples, for example, if these were toxicity studies. If an organism is exposed to a nanoparticle, we analyze the particle before and after exposure, and then use the FFF ICP-MS to determine what happened to the particles as they were exposed in the biological media. This has an added advantage due to the sensitivity of the ICP-MS, as we can detect nanoparticles at the part per billion range, therefore providing data at environmentally relevant concentrations.